This is the 2006 t-shirt.
Right. Well worn.
Yeah, exactly.
You have a shorter break.
That way they'll have time to get coffee without getting it.
Right.
Shall I go and call the rest of the gang?
Yeah, sure.
You can describe the ordering but I'm not going to do that. What is?
It's not very high, I know, but we want it to come down a lot. There's like up and then down and then up. Bring some robots to carry us up the mountain. It would be good. Oh, really good water.
Yeah. You're working on that. Okay.
And then there are like media products where it's like arm movement.
Slightly more awake. Ooh. Elbow pass.
Is it the? It's not the
No, that's floral. The floral's good. Oh my god. These are still sore.
I'm gonna read about
Sore.
this.
Just do this.
Okay, let's get started. Welcome back. So, before I get started on today's new content, which is about contact lines, which is about where three different phases come together. Yes. Oh, microphone. Oh, yeah. Sorry. Yes, I will try to. And you will remind me if I don't, or someone will. Okay. Okay, how's that? Okay. Okay, so yesterday we talked about where the interface between two phases, okay? Today we're going to discuss, and the interface between two phases is two-dimensional, right? Today we're going to look at the interface between three phases, which is one-dimensional, right? That's a contact line. So yesterday the key result for understanding the interface between two fluid phases is the Young-Laplace law. I wrote it up there. And just to remind you, it says that the pressure drop or the pressure difference across the interface depends on how the interface is curved and what the tension of the interface is. Okay? Now, this relationship is a local relationship. So if you have an interface everywhere on that plane, or not, it's not necessarily a plane, that two-dimensional surface, you can calculate a curvature, right? And therefore, you can figure out the pressure drop across that interface. Now, I want to talk a little bit about the assumptions here for this relationship. It requires that the two bulk phases on either side have to be fluid. Tomorrow, we will generalize that where either side, they don't have to be fluid on either side. This tension, which we use the symbol upsilon, has units of force per unit length. And the idea between Young-Laplace is you have a force balance between the force being applied at the boundary versus the force being applied across the face. Now, this Young-Laplace law, as written, works for any, as long as you have, if you have fluid on either side, and it always works if the interface between them is also fluid. It sometimes works when the interface between the two fluids is solid, okay? So it works for a spherical balloon, but it doesn't work for a cylinder. And if you look at the discussion problems, specifically problem number 2, it'll work you through why you can't use Young-Laplace. It's basically because if you have a non-spherical shape for a solid shell, you have to have, in order to satisfy force balance, the tension has to be anisotropic. And this relation assumes that the tension is isotropic, okay? So you can only use this when you have an isotropic tension, okay? And that usually is not the case for a solid. It only is the case in special cases. Funny way to say it. Okay. All right, so that's just to remind you about yesterday. Before I move on, does anyone have any comments or questions? Okay, great. So now let's talk about contact lines. Okay, so we're going to start off by doing a little thought experiment. It's hard to find big pieces of chalk. We should get some new supplies of chalk here. There's boxes. They're all okay. Now I know where to find the next one. Okay, great. So what we're going to do is we're going to bring together a puddle of liquid 1. Okay, so here is a puddle of liquid 1. Okay, if it's a puddle, what I mean by that is the interface is flat. And in order for the interface to be flat, gravity has to dominate, which means the droplet that this puddle came from had some radius that's much bigger than what we called the capillary length yesterday, which was a function of the surface tension, the density, and the acceleration due to gravity. Okay, we have a puddle, and now we have another droplet of a different fluid, an immiscible fluid. Okay, so what I mean by an immiscible fluid is that when you try to mix them, they stay phase separated. Okay, like oil and water. So I have a droplet of liquid 2, and that droplet is going to be so small that we don't have to worry about gravity. Okay, so if it was freely suspended, it would be, or if it was sitting on a surface, it would be a sphere or a spherical cap, depending on the boundary conditions. Okay, so what we want to do is we want to put these two together and ask what it's going to look like in equilibrium. Okay, so what we're going to assume at first is that all of the physics is contained in the surface tensions, right? There's going to be no other forces. There's no temperature gradients or electric fields or whatever as we someone's question yesterday. Everything's in the surface tension except for the gravity that's keeping this thing flat. We're only going to keep track of the surface tension. So we want to calculate the equilibrium shape, the equilibrium, let's say, surface tension dominated. And then I'll briefly discuss what happens when you have an external field. Okay? So what are the material parameters we're going to care about? Shout out the material parameters we're going to need. How many surface tensions are there? 3. There's 3. Good. Excellent. So we need the following material properties. Or here are the relevant surface tensions. Surface tensions. Okay. This phase out here is a fluid phase. I'm going to call it 0. We have the surface tension between the droplet and the surrounding fluid phase. We have surface tension between the puddle and the fluid phase, and the surface tension when we're going to be bringing these two into contact, so we're going to have to worry about the surface tension between the puddle and the droplet. Okay? Okay. So how can we calculate the equilibrium shape? Yeah, force balance. Yes. Yeah, excellent. So good. Yesterday you all shouted out, minimize the energy, right? But you can do that. And actually, we're going to do one method. We're going to do one energy minimization today. OK? And when in doubt, minimize the energy. Or even better, minimize the free energy. More general. OK, so method 1, we're not going to do it, but I'm just going to say you can minimize the surface energy with what constraint? Yeah, you gotta. These are incompressible, so you have to conserve volume with volume constraint. Okay. Now this is sort of the. I would say this is the first principles way of doing things. Okay. So it's very, very physical to say that you want to minimize an energy, right? That's great. You can't be more physical than that. But the problem with just starting here from first principles is that we ignore everything we learned yesterday about the mechanical stability of an interface and what I mentioned yesterday, which I thought you had learned in the fluid section, which is the mechanical equilibrium of a fluid in bulk, right? So what we're going to do. So this is a totally physical way of doing it from first principles, but we'll have another physical way, right? Which involves using what we've already learned about closely related problems. The key advantage of the second way is that the math is a lot simpler. Here, of course, the variational calculus could get complicated. OK, so we're going to do it a different way. And we're going to start method 2. That's the method we're going to use. We're going, as you all said, we're going to make sure the forces add up to 0. I'll just speak a little bit more generally, and I'll just say impose mechanical equilibrium on the bulk. That's the 3D part, right? And then we're going to impose mechanical equilibrium on the interfaces, which is the 2D part, and then we'll find that that's not enough, and we need a way of enforcing mechanical equilibrium on the contact line, which is the 1D part, OK? And that's where the new stuff is. But to remind you, or not remind you, I'll ask you, these are fluids. What is the equilibrium condition on the fluid, the bulk of the fluid? The pressure is the same everywhere, OK? Pressure is the same everywhere, and since there's no gravity here, or we're ignoring gravity, that means that the gradient of the pressure in each of the phases is equal to 0, right? The gradient of the pressure overall isn't 0, because every time you cross a curved interface, you get a pressure jump. But within any of those interfaces, right, the pressure is going to be uniform. OK. And then for the equilibrium condition for the interfaces, we have Young-Laplace. Okay? So equilibrium condition for the interfaces is Young-Laplace. Okay? So we have 3 interfaces. We're going to have the interface between 1 and 0. And the interface, Young-Laplace tells us that P1 minus P0 is going to be equal to gamma 1, 0 times kappa 1, 0. Okay? Now let's be careful here. Okay? So when I say kappa 1, 0, I don't mean tensor components. This can be one of those things that if you go back and look at your notes, you could get really confused. But really here, I mean the total curvature of the interface between 1 and 0, right? It's not the 0th and 1th components of the curvature tensor. Okay? So, so Young-Laplace tells us this, right? What's the curvature of the 1, 0 interface? 0, right? It's flat, right? So that tells us equals 0. So that tells us that the pressure inside the puddle is the same as the pressure outside. Okay? We've learned one thing so far. All right, so that was 1, 0. We've got 2 more interfaces. And I need a bigger piece of chalk. OK, yeah, let's do 2, 1 next. OK, so the interface between 2, 1, this is going to be the contact zone between the droplet and the puddle. Young-Laplace tells us that P2 minus P1 is going to be gamma 2, 1 times kappa 2, 1. But we've already learned that P1 is the same as P0. So this is just P2 minus P0. Okay? And we won't go any farther than that for now. Okay? We won't say anything yet about what this curvature is until we apply the boundary condition on the last interface, or not the equilibrium condition on the last interface, which is the 2, 0 interface. And the Young-Laplace on the 2, 0 interface says that gamma 2, 0, P2 minus P0 is gamma 2, 0 times the total curvature of the 2, 0 interface. All right, so those are our 3 conditions. And one nice thing is that this condition and this condition both tell us about the difference between the pressure of the droplet and the surrounding fluid, right? So this and this. So I can set them equal to each other. And that's going to give us a handy result for later, that the product of the surface tension and the curvature for the 2 and 1 is equal to the product of the surface tension and the curvature for 2 and 0. Okay? So that's going to be useful. It's not so useful that I'm putting a box around it, but it's useful for this problem, so I'm going to put a star next to it so we can refer to it later. So physically what this says is that the pressure drop across the 2-1 interface is the same as the pressure drop across the 2-0 interface. Okay? Why does it have to be true? Yeah, because the pressure of 0 and 1 are the same, and you have to have the same pressure everywhere inside of the droplet. That's the way to think about it. Okay? All right. So that wire is making me nervous. Okay. Okay. So now let's put the bulk condition together and the interfacial conditions together. Okay? The bulk condition says that we have to have, inside of each phase, it says we have to have no pressure gradients. Okay? That means, just like we discussed yesterday, the curvature on each of the interfaces has to be the same everywhere on that interface. Which means what about the shape of that interface? It's going to be spherical. It's going to be spherical. Okay? And yeah, so 2-1, the 2-1 interface and the 2-0 interface are spherical caps. So they're just parts of a sphere, okay? And the radii, or the relative radii of curvature of those two spheres is going to depend on the interfacial energies, whose radii depend on gamma 2,1 and gamma 2,0. Okay? So now that we've said that, we can draw our hypothesis about what the droplet's going to look like. Right? I intentionally did not draw the two next to each other because it was hard for me to draw it an ansatz without telling you the answer. So I'd like if you think about it for a second, okay? So I need the top and the bottom of the droplet to be spherical caps, but they don't necessarily have the same curvature. I need the rest of the interface to be flat. So this thing is going to look something like this. This is going to be hard to draw zoomed in. Okay, so this is supposed to be a flat interface, and these are both supposed to be spherical caps with different radii of curvature. Okay, so this type of shape has a funny name, which makes perfect sense. Does anybody know the shape of this? What this two spherical caps stuck to each other is called? A UFO. Yeah. What else does it look like? A lens. So people call it a lenticular shape. They make an adjective out of lens, lenticular. And from what I understand, though, this is hearsay. I haven't had a chance to confirm this. This is how people actually make small lenses, is by basically floating molten glass over something that molten glass will float on. But that's hearsay. So. Yeah, OK, there's no gradients in the bulk. So that means when you use Young Laplace, it says the pressure drop across the interface is going to have to be the same pressure drop everywhere across the interface. Yeah, the pressure is the same on all sides, so the curvature's got to be uniform on the interface. Thank you for your question. All right, any other questions so far? Yeah. We'll get to the contact line. Yeah, I have only talked about, when I say interface, I mean the two-dimensional object in between the two three-dimensional phases, right? I'm not saying anything about the contact line. So this is only true for patches, I would say, that do not involve the contact line. Good question. Did I answer your question?
Yeah, I would recommend like close to the contact line.
Yes. OK. So I would say that the deformation near the contact line in this problem would sort of be due to sort of have to be long-range forces or molecular scale type physics. At a continuum level, you should be fine all the way up, right up to the contact line. OK. Anything else? If there's just surface tension, which is scale-independent surface tension, it's going to be fine all the way up, right to the contact line. OK. Good. OK, so we have this shape. How many degrees of freedom does this shape have? I heard 1. I heard 2. So I've got one radius. I got the radius of 1, 0. I've got the radius of, no, that's not 1, 0. That's 2, 0. I've got the radius of 1, 2. And I also have like the height of 2, 0 and the height of 1, 2. So I have 4 geometrical degrees of freedom. These are geometrical degrees of freedom, right? So if I say I have a lenticular shape, I have to specify 4 numbers to nail the shape. OK? How many constraints do I have? I have 1 constraint. I only have 1 constraint so far. OK? So far, we have 1 constraint. Well, I shouldn't circle it. 1 constraint. And that constraint is star, right? That relates the radii of curvature or of the curvatures of these two phases. OK? There's one more constraint that you can get pretty easily. Volume, right? So the droplet has to, so far, 1 constraint. The droplets are incompressible. Also have conservation of volume. So that gives us 1 more. But Still need 2.
I don't understand how there are 4 independent degrees of freedom. Surely if it was an adjustment of the heights,
Yep.
then its corresponding radius would change.
Yep, that's a good point. No, because the other side could have the same contact radius for 2 different values of the height, unless it was at the equator, I think. Yeah, okay, it gives 1 more constraint. So the problem might end up being overspecified, because I'm going to give you 2 more constraints. But I think those 2 more constraints are probably going to end up, they're going to be explicitly, the constraint that we're about to develop on the contact line assumes that the 2 faces are meeting at the contact line. Right, so it's going to turn out if you did, yeah, so that's a good point. So you could enforce these 2 to meet at the same spot, but that would only give you 1 more constraint. You need more than that. So let's find out what more than that is, okay? But I think the constraint what we're about to do is consistent with that one, okay? So the point is we need to look at the contact line. Okay, and so what we're going to do is we're going to impose mechanical equilibrium at the contact line, okay? So mechanical equilibrium at the contact line. Okay, so let's zoom in near the contact line. Okay, so this is in here, out in the bulk, we have pressure 1. Out here, we have pressure 0. Out here, we have pressure 2. Okay, so we're zooming in at the contact line. And what I'm going to do is I'm going to draw a control volume. Okay, so I'm going to draw a control volume that looks like this. Okay, so our control volume is going to be a thin prism as shown. Thin prism as shown. Okay, so as shown, yeah. So this we see a triangle in this plane, but remember the whole thing has got radial symmetry. So what I'm going to do is I'm going to make this thing very, very, very thin in the orthogonal direction, so the contact line looks straight over that short distance, okay? So that's why we're using a thin prism, okay? So what we want to do is we want to look at all of the mass inside of this prism, and we want to make sure that all the forces add up to it, acting on it, add up to 0, okay? So we're going to need to, I want to specify a few sort of geometrical things first. So I'm going to call this normal off of my arbitrary little surface of my control volume here, and 0. I'm going to call this normal n2, and I'm going to call this normal n1. And I'm also n1 hat, sorry. So those are the normals off of those facets of my rectangular prism. Not my triangular, whatever it is, a thin prism. Okay, and then I need to specify some other directions too. I need to specify with unit vectors the directions of the interfaces. Okay, so there is the tangent to the interface 1, 0, I'm going to call T10 hat. The tangent to the 2, 0 interface, I'm going to call T20 hat. And the tangent to the 2, 1 interface, what am I going to call it? Thank you for not falling asleep. Okay. Okay, so those are that's everything so that we've sort of fully specified the geometry, and now it will be relatively easy to calculate the total force. Okay? So we want all the force to add up to 0. Okay? So there are 2 different types of contributions to the force. What are the 2 different contributions? There's pressure, right? So the pressure is going to be acting from the outside, and there's also going to be what? The tensions, yeah, the surface tensions. So the total force, so let's do the pressures first. All the pressures are pointing inward, okay? So the total, the force on, hello?
These tangent vectors,
Yeah.
they're defined at the
Yeah, exactly, because as I've drawn it, these interfaces are still a little bit curved, so they're really defined right at that point at the end of at the edges of my control volume. Anything else? Yeah. No, they're not. Yeah, they're parallel. They're parallel to the interface, right? Anything else? All right, so let's do the forces from the pressures. The pressures are all pointing inwards. So if we call the area of the facet against 0 A0, then it's A0 P0 N0 hat. And it's minus N0 hat because it's going inwards. And then I get the same thing for all the other facets, but where you change the number. OK, so minus A1 P1 N1 hat minus A2 P2 N2 hat. And now we extend to the next line plus the surface tension term. So what do the surface tension terms look like? Someone shout out what a surface tension term is going to look like. Yeah, so I'm going to have, let's say, gamma T10 hat plus gamma T12 T, or am I saying 1, 2, or 2, 1? It doesn't matter, but I just want to be consistent. They're the same. I mean the same thing when I write them. T21 hat plus gamma, what's left? 20 T20 hat. OK, I have one little problem I have to fix. Units, right? So I need to put in the thickness out of plane, right? So let's call it D. So the thickness out of plane is D. So this is the out-of-plane thickness. Out of plane thickness. D. Okay. D is already hiding in A0. So A0 is like the length of that line times D. Yep.
So the force balance will be from the surface of the control volume.
Yeah.
Okay, and the pressures are on this side, and then the
Yeah, so the pressures act along, the key thing here is the pressures act along the facets, and the tensions act along the corners. Yeah, so that's the real kill thing. What?
and these corners are lines because this has to be dimensions.
Yes, exactly. Yeah, they are lines. Yes, exactly. And that's why we're multiplying them. Oh yeah, so they're not the corners, they're the edges, right? So the pressure's acting on the facets. The tensions are acting on the edges. And that's why I have the factor of D there. Thank you for clarifying that. Any other clarifications? OK. Now, this next part really makes me feel like the theorist that I'm not. OK? So the n hats? Yeah, so I just arbitrarily drew like straight lines from one spot on one interface to another spot on the interface. And n hat is just the normal to that line.
Once you draw the dotted line, I guess another way to say it, what's the difference between dotted line? What defines the point?
I can draw, well, OK, so right now, the answer that I'm getting is going to depend on how I draw the dotted lines. But after I do the magic that I'm about to do, which makes me feel like a theorist, OK, then how I drew those dotted lines will not matter at all. OK? So that's why I did not specify them, because we don't need to. OK, so now scale the volume by a factor lambda. OK? So imagine that I just have my volume, and I'm going to either make it twice as big or half as big or a quarter as big. OK? Now, if I take the limit, and the limit as lambda goes to 0, what happens to my equation? the pressures get arbitrarily small compared to the tensions, right? So I can completely forget about the pressures. That's the point, okay? And I can also forget about this d, which also got scaled out, okay? So we get that gamma 1, 0, t hat 1, 0, plus gamma 2, 0, t hat 2, 0, plus gamma 2, 1, t hat 2, 1 equals 0, okay? Now this gets a box. Yeah, yep. Yeah, exactly. So what I'm doing is what I mean by scaling the volume, I'm just zooming in. If I zoom in really, really, really closely to the contact line, a few things happen. My lines get straighter and straighter. The interface lines get straighter and straighter. And the amount of area I have shrinks a lot faster, the amount of edge length I have. And so the only thing that's left is the tensions. The pressures go away. Yeah.
Why didn't you just start with looking at the single point at which they all contextualize?
Because people do that all the time, and it drives me and lots of people crazy, okay? And I'll explain why. A lot of people, well, they're often going to say, well, I'll get there in a second. I'll get there in a second. So what does this, I was somewhat careful, okay? At least extremely careful for an experimentalist in deriving this expression, okay? Okay, now let's talk about the interpretation of that question, and then I'll address exactly what you just said, okay? So I'm basically trying to prove the crap that people always say, which happens to be correct, but confusing. Yeah. Yeah, so no, because as lambda goes to 0, eventually they've got to be straight, right? Because eventually the expression, I'm assuming the interface is continuous. If the interface is continuous, I think mathematicians, then I think it's got to be locally straight or locally flat. Yeah, so there could be molecular scale stuff. Okay, so this is cool. A great question. I understand the source of your question now. So this relies on the fact that there's a separation of scales where we're zooming in like at a much, much higher than the radii of curvature, right? So we can't, all of the radii of curvature macroscopically that we see basically are negligible and all the interfaces look flat close enough. But yet we're not zooming in so much that we have to worry about intermolecular forces. And that's sort of the separation of scales. All right, I'll have you hold that thought and let me know if you want to join. Bring it back. So actually, sorry, I don't know your name in the front who asked me that good question about Andrew. So since I think you sound like you're, so how do people normally, what's the interpretation of that equation? Oh, you don't know. OK, so what people normally say is that they actually derive that just by saying right off, the forces on the contact line have to add up to 0. OK? But so that the interpretation is that the forces on the contact line, the forces or surface tensions or tensions at the contact line must add to 0. OK, so they show the contact line as a dot here, and a vector corresponding the force due to this one, the force due to this one, and the force due to this one. OK? I'm not going to put those in yet. OK? So the thing that always bothered me about it is it smells right, but it doesn't, it's not super convincing. Because why do forces have to balance on something that has no mass? A contact line has no volume, right? So it's not obvious to me that the forces have to balance on an ideal construction that doesn't exist. right? So this way, at least now I tried to argue that in the limit, as the area around the volume gets really small, it looks like the forces are balancing on this infinitesimal idealized one-dimensional object. Okay? So this thing that people always say is totally kosher, right? It might, but even though it sounds like it's not kosher because you're adding up forces on something that has no mass, it's just fine. And maybe I'm making a big deal out of nothing, but it's always something that bothered me, and giving these lectures is a great excuse to scratch my itches. Okay?
Say not having mass is actually better than having mass. If you have a mass, then that mass can accelerate, and then the force.
Yeah, exactly. So at the end of the day, it's awesome that we have this contact line that is infinitesimally small.
Right, then it's actually better.
Yeah, exactly. So I just wanted to argue that idealization makes sense, like with respect to the macroscopic picture, right? So it makes sense in the limit as we make the volume really small. So that idealization is good. And yes, it is better than keeping track of the mass. It's much, much better. It's just like if you put a vortex in a superconductor, you don't worry about the core, you worry about the far field stuff or something like that. Not that I know and understand any of the words that I just said. Okay, so the point here is that for given values of the gammas, in order for the forces to balance, the interfaces have to meet at fixed angles. Okay? For given values of gammas, there are unique values of alpha and beta. Okay? So that means the angles between the interfaces are fixed. Okay, and this finding comes from someone named Neumann, and I think this is the same Neumann from the normal Neumann boundary condition, right? Instead of sticking the value somewhere, you fix the slope. That's sort of what we're doing, right? We're fixing the slopes, and we're saying the relative slopes of these lines have to be the same. Okay, so how many more constraints has this given us? Alpha has to have a certain value. That's one constraint. Beta has to have another value. That's another constraint. We now have enough constraints to fully specify the shape of the droplet. Okay? I think, well, here by construction, we're assuming that those two sides are meeting at the same spot. So Andrew, I think his name is, suggested that you could get a constraint by just forcing them to meet at the same spot. But that would only give you one. Here we assume from the beginning they're meeting at the same spot. And we also got another thing. That ended up being expressed as two angles, which gave us more information. So the key thing is to specify the shape of the droplet. We had to impose equilibrium in bulk in 3D. We imposed equilibrium on the surface interface in 2D, and equilibrium on the contact line in 1D. Okay? This looks like a point. It's actually a line, right, because it's going at a point. So let me get a chalkboard ready. And I'm creating a dramatic pause of silence because I think the thing that I'm about to say may be the most important thing that I'm going to say in all three of my lectures. Though I'm not sure that I'll say it well. I just know it's important. The light switch? Oh, that's what this is for. Oh, yes, thank you. Oh, thank you. Is there one over here too? No? Darn. OK, so this is the important lesson. OK. This gets 2 stars, OK, in a box. The contact line is singular. It's singular in a physical sense. What do we mean by when we talk about singularities in physics? Things blow up, OK. That's one particular thing. It's not what I mean here. That's more of the mathematical thing, but what's the physical implication that you often have in a singularity? Yeah, we have discontinuities in the density, right? We have a line where there's a discontinuity in the density that's three-way. So I guess that's the derivatives of the density blow up. There we go. It's a singularity. Length scale goes really small, but what's the useful thing about singularities? What happens? Scale free is good. Yeah, think the solution near the singularity is scale free. Super duper 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 important. OK, that's awesome. That's not the point I was going to make, but that's true. Phase transition critical points. That's one example of a singularity. That's not a singularity in physical space. It's a singularity in phase space. And what's the awesome thing about a singularity in phase space? Universality. What does that mean? Yeah, exactly. So if you draw the phase diagrams for all the different gases, right? Far away from the critical point, they all look different. But when you line them up at the critical point, they all look exactly the same. OK? And because they only the key, and that's because the contact line is singular, and that means, and I'll say I'm talking specifically here, but I mean it generally, its structure depends only on what we'll call local physics. Okay, and what I mean by that is that the structure of the singularity does not care about far field boundary conditions. Okay. So here, what I mean by the far field boundary condition is that this contact line condition that these three interfaces meet each other at the same angle is independent about how big either one of the droplets is. Okay, it's independent of whether or not I have gravity, right? Because gravity scales like volume. So if I get really, really close to the contact line, I can forget about gravity. All of the local physics is encompassed in the competition of the surface energies. Okay, so the key thing, yeah. So it depends on the local physics, and here the local physics equals the material properties, and the specific material properties are the surface tensions. So that means if you want to learn about, let's say you have three phases of liquid, and you want to learn about something about their material properties by putting one drop of a liquid on top of another liquid, if you want to learn something that's independent of the size of the droplet, i.e. something that tells you something about the materials you're looking at, not the geometry of your problem, you want to look at the contact line, because that's the part that's singular. Okay. Exactly. As long as you look at the right thing, you're going to be OK. All right, so that's really important. That's really, really important. It's worth, how much time this might be the perfect time to take a break, but let's take a question before we take a break.
So is all this just assuming still that we stay at a scale where we're not looking below the capillary length?
So we are way below the capillary length, right? Because we're explicitly like where gravity doesn't matter, right? But we're still above molecular length scales, right? So this, like every divergence in physics, it ultimately breaks down, right? If you get too close to the contact line, you can see the molecules. And so this doesn't work anymore. Okay? All right, so let's take a 5-minute or I'm going to say 3-minute break, because last time I said 5 and you took 10. Okay?
So I guess I was sort of expecting that we would find that there
because people can't hear me shouting through the internet. Okay, so we're going to talk about some limiting scenarios. One interesting limiting scenario happens when the tension, the baseline tension of the puddle is really big, and specifically when it's bigger than the sum of gamma 1, 2 and gamma 2, 0. Okay, what happened? What's the problem then? What problem do I have when gamma 1, 0, is too big? What? Yeah, no, okay, yeah, or just purely mathematically, when I add up these vectors, I can't make this one plus this one add up to this one if this one is bigger than the sum of these two if they were in a straight line, right? So what that means is that the thing wants to completely spread. We could call that complete spreading. That's sort of the language that people would use for liquid on liquid. It's analogous to what people would say for a liquid on solid, which they normally call total wetting. Yep.
So in the surface tensions we have,
Yep.
we're assuming that volume tends to 0.
The volume
Volume of this.
of the contact line it tends to 0. Yep. It's idealized as a line.
There's only one out of plane component, which is surface tension to 0.
Yep.
Everything else is in plane.
Yep.
How do we balance the vertical component?
No, we have two out of plane. We have this one and this one.
Uh,
These two can balance each other just fine.
oh, it's not in the same plane. Okay, because it's
No, sorry, this one has an in-plane component and an out-of-plane component. This one has an in-plane component and an out-of-plane component. So these two on their own balance the out-of-plane part, and then both of these together balance the in-plane part. Yep.
But they're all on the plane of the board.
They're all on the plane of the board. Yeah, they're all on the plane of the board. Thank you. OK, so what total wetting looks like is when we have 0 on top, we have our fluid on top, then we have basically a puddle. Now, of our droplet becomes a puddle. Oh, that's 2, not 1. And then we have our initial puddle. OK, the first puddle was created by gravity. The second puddle was created by surface tension. And you can also this can make sense if you just look at this. If this, it makes sense that if the energy of this bare interface is really high, and it's higher the energy of this interface plus this interface, then it's worth it to create both of these interfaces so that you can cover up this one. Right? Does that make sense? So what determines the thickness of 2? Volume conservation. What other guesses? But what if I have an infinite? So if I have some finite dish that I'm doing this in, it'll spread to fill the finite dish. But what if I do it in an infinite dish? How big the atoms are? Yeah, so molecular stuff. OK, molecular scale forces. Yeah, they do. And if you want to learn about how that works, then I think that is the de Gennes contribution to the de Gennes, Curie, and Brochard book. Yeah, just so there's like a few chapters. I'm pretty sure that's the de Gennes. Those are the de Gennes chapters of the little white book. Yeah. All right. OK, so quickly, let's just discuss a couple of other limiting scenarios. When gamma 2, 0 is much bigger than gamma 2, 1 or gamma 1, 0, that means you want to completely get rid of the interface between the droplet and the surroundings. So what happens is the droplet gets completely sucked into the puddle, OK? And if gamma 1, 2 is bigger than gamma 2, 0 plus gamma 1, 0, that means similarly that you're going to want to completely get rid of the interface between the two liquids, and then the droplet will sit on top of the puddle with arbitrarily small contact area. OK? Yeah. Oops, sorry. Thank you. That's what we're talking about next. Yeah, absolutely. So we're going to talk about that's what we're going to talk about next. Not quite next, but nearly next. I just want to say one quick thing about the effect of gravity here. So the effect of gravity, so if you're not in one of those limiting cases, then you get something that looks like a lens. And if you have something that looks like a lens, okay, if you start with a lens-like solution and you add gravity, and what you end up getting is that the droplet wants to flatten out because it wants to be as close to the center of Earth as possible, right? And actually, I'm going to have this. So the thing end up more like a penny instead of a spherical droplet. It flattens out on both sides. But the key thing that I want to point out is, what do I want to point out? This angle is, if you zoom in close enough, right? If you zoom in close enough, you should see the same exact angles that we saw before, okay? So that's, again, the point that I'm making about the singularity is it doesn't care about far field boundary conditions. It also doesn't care about body forces for these mechanical singularities. Yeah?
Can you take advantage of something like that? So say I have a ionic droplet.
Yeah.
I want to figure out how ionic it is. Can I see how close I have to get to the singularity before I recover that sort of singular behavior from about charge position on it?
Yeah, so I would say, I think it would be how close you have to get to it before it stops working, as opposed to when it starts working. Yeah, absolutely.
Can I exploit that singular boundary?
Yeah.
Those kind of formulas?
Yeah, absolutely. 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 And I think guidelines for doing that would be in these nice chapters, which I think are by Dijen in the Dijen Carré Brochard Wyard book. Okay. So now, let's do exactly what he just asked about a moment ago, which is what happens when the droplet is on a solid surface, okay, as opposed to a liquid surface. So we're going to do contact between a liquid droplet. This is going to be a lot more familiar to most of you. And I will hopefully illuminate some ways that people sort of think sloppily about this, that give them the right answer, but then make it confusing for other problems, okay? So we want to look at the contact between a liquid droplet and a rigid solid. Okay, tomorrow we'll talk about contact between a liquid droplet and a deformable solid, but here it's rigid. We're just going to assume it's ideally and it's ideal, and it's not at all deformable. Okay, so if we're in the surface tension dominated limit, you can make all the sorts of arguments that we've been making before, that this thing should be a spherical cap. Okay, so I'm going to label the substrate as S for solid. I'm going to label the liquid as L for liquid. I'm going to label the surroundings as V, traditionally for vapor, but it actually could be a liquid with perfect generality. Nothing I'm going to say later changes. Actually could be a liquid. As long as it's immersed in the fluid, it's fine. Okay? So we have a solid, a liquid, and a vapor, and you can make all the arguments that we make about mechanical equilibrium of the bulk, requiring the pressure to be uniform, mechanical equilibrium of the interface, requiring the curvatures to be uniform, and we conclude what about this droplet? It's a spherical cap, okay? So it's a spherical cap. The spherical cap has two parameters, right? It has let's say, the radius of curvature. Spherical cap. It has two free parameters instead of four. And they are the radius of curvature, which I'm going to call r, and theta, which is the angle at which the spherical cap hits the flat interface, the solid interface. Okay? So that's all you need geometrically to specify the shape. Okay? So how are we going to get rid of those two free parameters? There's one that's really easy and very general. Oh, you don't, because this one is forced to be flat. Yeah, by saying that the substrate is rigid, then it enforces that what we were calling beta is always 180 degrees due to the rigidity. So I heard someone say the answer to my question, what trick can we use that's very general for a liquid to get rid of one of our constraints? Yeah, volume conservation, OK? So volume conservation gets rid of one degree of freedom, one geometrical degree of freedom. How are we going to get rid of the last one? Contact line, something about the contact line, OK? So what are we going to do explicitly? We're going to zoom in and we're going to do what? We're going to assume it's singular now, because we are. And I don't have time to mess with arguing, but by analogy to the liquid case, we're just going to assume it's singular. And then we're going to look in really close. We have our theta. We get close enough that everything looks straight, but not so close that you see molecules and stuff. So we've got solid. That's not the solid. That's the liquid, and that's the vapor. And that's the solid. OK? And then how am I going to figure out what theta is? Force balance. OK, let's try that. That's what I always try. You guys always want me to do minimization of energy. OK, so let's do force balance. The derivative of energy is force. Well, anyway, we'll see in a second. They're closely related, but they don't always work the same. Anyway, SV. OK, so I've got 3 forces acting on that contact line. What do I need to do to balance the forces on that contact line? What? Yeah, you need another force. Do we have any other forces? We have a normal force. Sure. Do I have any idea what its magnitude is? No. I could pretend that there's some normal force and I don't know what its magnitude is, and then balance the in-plane force, right? And then it turns out you would get the right answer. Oh, actually, sorry. Sorry. Let me fix something. You would get the right answer. I need to fix something. I got it right in my notes, but I wrote it wrong on the board. These should be upsilons, not gammas. OK? Because we're talking about forces. And the force per unit length is only equal to the energy per unit length generally for a liquid. It's not generally true for a solid. OK? So, but if you balance the in-plane forces and you assume that the solid surface tension is the same as the solid surface energy, you will get back the right answer. OK? I don't like that because you first of all have to assume that the solid surface energy is equal to the surface tension. And the other reason I don't like it so much, I mean, it's right. It gives you the right answer. It's just really an aesthetic thing, is that if I was teaching freshman physics and someone told me balance the forces by only balancing one component in plane, I would tell them they were wrong. OK? I don't like leaving things unbalanced and then just saying magic takes care of it. OK? So I'm going to do what you all wanted me to do originally. I'm going to minimize the energy. OK? I just made a really hard argument to convince you should have done what you thought I should have done if you hadn't heard me talk before. So let's minimize the energy. So anyway, you can get the right answer if you balance forces in plane and assume the stress is equal to the energy. But let's do it a different way. Minimize the energy. OK, so the trick about minimizing the energy here is you got to come up with a nice way of formulating the problem. We could minimize the energy for the whole spherical cap, right, and do some relatively tricky geometrical variational calculus. Or we could try to minimize an energy more locally by being a little bit tricky about how we set things up, but I think perhaps still rigorous, and get the right answer. OK? So what I'm going to do is first I'm going to draw my flat solid surface, and then I'm going to draw my liquid vapor surface coming into contact at some angle theta. And this is my vapor. And this is position x. OK? Now what I'm going to do is I'm going to fix this point on the liquid vapor interface far away from the contact line. OK? And then I'm going to allow the point of contact to vary. Here I can consider x plus dx, right? And there's some other, actually I'll call this theta of x. And this is theta of x plus dx. OK? And now I can find the value of theta. I'm going to find the value of theta, or I'm going to find the value of x that minimizes the energy. OK? Now, it might seem sort of weird that I'm sort of artificially fixing some point of the contact line and let it very far away. But I'm going to wave my hands, and I'm going to say, well, because it's a singularity, the answer I get shouldn't depend on the far field boundary conditions. Right? Fixing it at some point far away is just a far field boundary condition. OK? So it's perfectly kosher. OK? The key, I think. And the key assumption here is that there's some sort of reservoir of liquid over on the left where you can pump more fluid in to let the contact line go back and forth. OK? And that reservoir would be like a droplet. OK, so let's minimize the energies. OK, so what we want to do is we want to calculate the energy, the derivative of the energy with respect to the position of the interface, which we're going to call x. OK? And again, we're going to have some volume out of plane. And I'm going to call that d, because we're going to need areas. And inside the bracket, we're going to have the solid vapor surface tension times the change in the length of the solid vapor tension with respect to the position of the contact line, plus the surface tension of the solid liquid, or the surface energy of the solid liquid interface, dl SL dx, plus gamma LV d LLV dx. I'm assuming that epsilon, oh no, I don't need to because I'm minimizing an energy. Thank you very much. So that's conceptually one reason that I really like for doing it by minimization of energy here, because in general it's not true for a solid that the energy and the stress, so the tension are the same, right? So I'm choosing to minimize an energy instead. It's more general and it's safer. Thank you for asking that great question. Any other questions? Oh, the question, what was your question again? Oh, yeah. She asked, did I assume that gamma SL and gamma SV were equal to epsilon SV and epsilon SL? And I did not assume that because I don't need to, because when I'm minimizing an energy, I care about the energy, not the force. And in general, I don't know whether or not those two are equal, so I don't want to make that assumption. It's an excellent question. OK, so just to be clear, what I mean by, I'll just draw one of them. What do I mean by LLV? I mean this, right? So it's the length in plane of the liquid vapor interface. That's what I mean by LV. Are there two here? Oh, I'm already on the second one. OK. Yeah, any questions? While I erase? Uh-huh.
LSL measured from sort of tablets and then
Yeah, some point really, really far away, but at the end of the day, the answer only depends on derivatives, so I don't care where the end is, as long as it's far away. That's why I started with the derivative right away, so I wouldn't have to worry about specifying the end. OK, so let's evaluate these derivatives. L SL dx. What's dl SL dx? LSL is this length. What's the derivative of that with respect to x? It's actually 1, right? Because it's dsL dx, so it's just 1. Then dl SV is what? dx is -1. OK? Now dl LV is just only ever infinitesimally harder. We need to use Pythagoras' theorem, OK? And we're going to have to specify momentarily the height of where we're fixing the interface. OK? And to apply Pythagoras' theorem, we get h squared, h squared plus LSL squared equals LV squared. That's thanks to Pythagoras, right? And now I can differentiate that. This is some made-up constant. I hope it disappears in my answer. It's going to, because now I'm going to take a derivative. So I get twice LSL dL SL dx is equal to twice what? Sorry. No, hold on a second. Oh, this is wrong. I could call it LSL, but I mean to call it x, right? X is the distance from this point here to down here. LSL could actually keep going forever in that direction. X is finite, and it goes from underneath here to here. I meant x squared instead of LSL squared. It's just part of that interface, right? So so now I differentiate the left-hand side. I get 2x, and that's equal to 2LLV dLLV dx, right? Mm-hmm. Yeah. I mean I just mean from here to here, from the point where I fixed the liquid vapor interface. There's no liquid vapor interface over here, or we're not changing it as we're pulling it out. And so that tells us that dLLV dx is equal to, is it LV over x or x over LV? X over LV, x over LV. And what's x over LV? LV, sorry, LV. Cos theta, trigonometry. You guys can do really fancy math. Don't forget how to do trigonometry. That's equal to cos theta. OK, so now we're basically done. OK, I need my next page. OK, so we just plug that in. dE dx is equal to 0. And so we get minus gamma SV plus gamma SL. And then we get a plus gamma LV cos theta is equal to 0. OK? Or you can rearrange that to solve for the contact angle, and you get cos theta is equal to gamma SV minus gamma SL over gamma LV. OK, this also gets a box. This is called the Young-Dupré relation. If you're British, you call it Young's law. If you're French, you call it Young-Dupré. OK? If you talk to French people about this problem a lot, you say Young-Dupré. Yes? Oh, the D, it's just a prefactor in front of everything, and I get a 0, so just divided it out. No, oh, sorry. No, it's just the depth. Yeah, sorry. OK, so that's Young-Dupré. And how are we doing on time? We have, 10 minutes? 10 minutes. OK, so let me just take a breath and figure out what I'm going to do. OK, that's good. Yeah. OK, so just like the liquid case, the answer we got is respects the singularity of the problem. We have divergent density gradients. OK, we need to have an answer near the contact line that only depends on local physics. It only depends on local physics, right? This is an expression many of you have seen before. OK, and if you have seen it before, you've usually seen it by just balancing the forces in plane and assuming that this is equal to the interfacial energy. This is a slightly more rigorous proof, and you get the right answer. OK? Questions? Yes? Yeah, that's what I'm talking about tomorrow. Yeah. Thank you. I asked myself that question 8 years ago. Yeah. And I've spent way too much time thinking about it. Yeah. Oh, well, I mean, I guess so there is an unbalanced normal force, right, which is gamma LV sine theta, right, in this thing. So what opposes gamma LV sine theta? We'll talk about that tomorrow. Yeah. So the forces do have to balance. And on a perfectly rigid substrate, it's sort of like, it's weird because a perfectly rigid substrate has no degrees of freedom elastically, right? Or you could say it's infinitely strong. And so anyway, it's hard to think about on a rigid substrate, but it's much more concrete on a soft substrate. OK? All right. So let's, just like before, there are interesting limits about the relative values of these. But in the interest of time, I'm not going to discuss them now. But they're perfectly analogous to the limits I discussed before. When the solid vapor surface tension is really, really high, the droplet tends to spread arbitrarily, right? When the solid liquid surface tension is really, really, really high compared to the other ones, the droplet doesn't wet at all, and it has just a little contact spot on the bottom. And when
They can't be equal. Physically, I can't think of.
What? OK, well, there's this funny thing about this is equal to a cos theta, right? So
I mean, it can't be 90 degrees.
no, they can be. It can it can totally be 90 degrees. I'll show you lots of data tomorrow that's 90 degrees. Yeah. Yeah. So anyway, there is a total spreading limit. There's a total total not sticking limit, and then there's something in between, which is what we've mostly been analyzing. Okay. We're assuming here that it's somewhere in between. So now that we've talked about the singularity, though, I want to talk about one specific geometrical implication, and I will erase the boards while you ask your question.
So if I may, gamma LV arbitrarily small.
Uh-huh.
Then you don't have a solution for that.
Gamma L, yeah, and then, yeah, so, OK, because here I've assumed what we call partial wetting, so that there's a contact angle. What happens practically is it completely spreads. Yeah. So this derivation actually only rigorously holds when you assume that there's some angle. And if it completely spreads, there's no actual contact line anymore. I assumed that there was a contact line. But if gamma LV is really, really small, it spreads forever, and there's never really a contact line anymore. OK. So now let's briefly discuss the contact of a rigid sphere. So this is like an elastic droplet on a liquid puddle. OK, so here's my sphere. But now my sphere is a solid, not a liquid. And here's my puddle. And it's a liquid. And I'm going to put them together. What happens? What's the equilibrium state? It sinks. How far does it sink? So let's say gravity doesn't matter. Let's say gravity doesn't matter. Let's say they're perfectly density matched, so you don't have to worry about gravity. OK, let's say this is another liquid out here. This is this liquid and this liquid, liquid 1 and liquid 2. They're perfectly buoyancy matched to this, and that's buoyancy matched, so we don't have to worry about gravity. OK, let's buoyancy match everything and put the solid sphere in contact with the liquid interface. What does the answer have to be? Yeah. Thank you. Yeah, because the contact line is singular, right? It only cares about the local physics. I just gave you some complicated version of a far field boundary condition, right? But at the end of the day, what happens is the thing sinks in far enough so that the angle between the liquid and the solid satisfies the Young-Dupré relation. Okay? And there's one nice thing about this is that because of the symmetry of a sphere, you can satisfy this without deforming the interface, which makes it easy. Okay?
How shouldn't there be two angles that it has to satisfy?
There's only one angle it has to satisfy because this is rigid.
And what's the outside?
It's another liquid or vapor.
So is this similar to how, like, in Hertzian contact, like rigid on elastic is an elastic on elastic match to each other?
Actually, that's so.
Like you can
I-
turn elastic into a rigid on elastic.
I have a lot to say about that. And I'm not going to say any of it right now because once you get me started, I'm not going to stop, and I'd rather, and it takes us somewhere else. So let's do it over coffee or something. Okay. I'm writing a paper about that right now. Okay. Yeah. So.
So the sphere adjusts its position until it finds the right.
Yeah, it adjusts. The sphere goes up and down until it finds the right angle. If you put a cube, then it gets funky, right? And that's something I didn't get a chance to talk about, is that if you have a flat surface and you can have a well-defined contact angle on this face of the cube, you have this face of the cube, you can have some well-defined angle on this face of the cube, but on this corner, you can have any angle you want, basically, between this angle and this angle, right? And because of that, if it's an infinitely sharp corner, basically. And because of that extra degree of freedom on the corner, things often get stuck on edges. That's called pinning.
With this situation, would it only deform the surface if you were taking into account gravity and other?
Any external force, yeah. If there's an external force, then the interface gets deformed, absolutely. Okay. So I'm going to show you just some. Okay, so just because it's fun, I was going to tell you all about implications. Okay, so let me just say really quickly, for droplets on a rigid surface, there's sort of two basic regimes. When there's a finite contact angle, we call it partial wetting, and if the wetting fluid is water, and the contact angle is 180 degrees, so this is partial wetting. People call this super hydrophobic, right? And it's sort of tricky just by playing with surface energy to make something super hydrophobic. In practice, you have to change the surface topology at really small length scales compared to the size of the droplet. We're not going to go there. It's discussed in the Degen book, and it's a huge area of research now. But what I want to discuss briefly is that there's huge dynamical consequences for how these droplets move when you force them externally, okay? So I'm just going to play a movie and wave my hands, so relax, okay? You can put your pens away. So if I put this droplet that has a contact angle of 180 degrees and I tilt the substrate, how does this droplet move? It can just roll, basically, because there's basically zero contact area between these two. Nothing, it just rolls, right? But if this guy, if you tilt this thing, it has to slide. And one thing that's funky that happens is that you end up breaking Young's condition because you're not in equilibrium anymore. Okay, so there's a different angle in the front and the back. But the real problem is if this is moving at some finite velocity, what's the velocity of the fluid on the surface of the solid? 0. So the velocity, if the droplet is moving, the surface of the droplet is moving at velocity v everywhere on the surface, right? But so what's the shear rate? So the shear rate goes to infinity here as it gets arbitrarily thin. So there's a divergence in the viscous stress, which people worry about. There's a singularity, which lots of people have worried about how it gets cut off. It used to be a huge area of research. I actually don't know what the answer is. But the point is, because of that stress divergence, this thing moves way more slowly down the surface than the one that doesn't wet. And so this has been a topic of active research, and it's still a topic of active research. But that active research has been so successful that it's now like commercially a thing where you can buy stuff to make your surfaces super hydrophobic instead of like partially wetting. And I'm going to show you a commercial. I have no financial interest in this company. I just found that I wasn't trying to find a commercial. I just found what I found for a company that sells you a coating. So first, let's look at. We're going to jump to 2 minutes and 49 seconds. 2 minutes and 49 seconds. There's all sorts of really cool tricks they do, and I'm only going to show you one of them. So if you put let's jump to 249. OK, so, oh, no, I don't want strainer turned into a cup. No, I want 249. OK, so I'm going to take a Petri dish, a regular Petri dish, and I put a drop of blue water into it. And see how it's tilted and the stuff is sort of hanging down. It doesn't really move, but it moves really slowly. And if this person sort of shakes it up, the droplets don't really move very much, or they move really, really, really slowly. OK, that's what normally happens. That's what you've seen forever. Now we're going to go to 2 minutes and 40 seconds. Is it 2 minutes and? No, 2 minutes and 20 seconds. This is a really fun commercial to watch. They should show it on the Super Bowl for scientists. Now they spray the surface. The surface, you notice the surface here is white because the surface is rough, and roughness is really important. And you put a drop of water on this super hydrophobic surface where the contact angle is 180 degrees. And the droplet basically can't sit still because it just rolls all over the place. And I think that's really neat. And if you play around on YouTube and you just put in super hydrophobic, there are so many actually products now where like people are, like I saw one on Kickstarter where someone was like, you could buy a super hydrophobic T-shirt, you know, so you can go out in the rain in the Boulder summer school and not have to, you know, get soaking wet. So anyway, I just wanted to end with a fun movie, and that's a direct consequence of, you know, all that contact angle stuff I was saying. Okay, thanks a lot.
Your name is not on the roster on the web page, and I don't have your name on the T-shirt. So if you want your name on the T-shirt, come speak to me now, because we're going to send it to Leo very soon. Are we doing a vote?
There is no vote. People who design have a vote.
So, hi.
Yeah, hey.
Again. So can we talk over lunch?
Yeah. Yeah, sure. Sure. Good. Yeah. Just hang out and see. Let's see if anybody has questions about the lecture, and then we can walk over to lunch. Yeah. Yeah.
So there's this interesting, there used to be this interesting field where people were studying coffee ring effect,
Yeah, sure.
which is based on, again, deepening and pinning and deform.
Yeah. Yeah, sure. I know all about that. Yeah.
I don't understand how the coffee ring effect forms.
Ah, got
It says
it.
that there's a pinning angle
Yes.
which induces an internal evaporation, induces motion within the bubble,
Uh-huh.
and that angle keeps on decreasing,
Yes.
which causes, but if the angle is continuously decreasing at the pins,
Yes.
then the point should move in.
Uh-huh.
But the ring remains at the same point,
Yes.
so I don't understand.
So the argument that people make, okay, for the contact for that problem, for the coffee ring, is I have a droplet, and it's pinned at some spot here.
Yes.
And we're going to evaporate our fluid, right? And as we evaporate fluid, that means that since there's a flux, there's a factor. Okay, so the physicists love the fact that there's an evaporative singularity here, but it turns out that you actually don't need an evaporative singularity.
Okay.
So, but we'll just say that because it's easier.